Area under a curve and antiderivatives, right? So far we've estimated the area under a curve by summing up the area of n trapezoids of equal height. Then we switched that up and we calculated the area under a curve by using limit and the area of rectangles, aka a Riemann sum. But we can look at this another way. So let's say we have the graph of a function y equals f of x, where f of x is greater than 0 in this interval from a to x, and that's what's shown. The area under the curve of f above the x-axis and between a and x is represented by the function a of x. So area of. What happens if we go beyond x? So as we move along, what's going well, so let's say we add a little rectangle whose width is h. So what's that up here? That's h, which makes this point here x plus h, right? So we moved along a little bit h. And if we have a really small h, then we're going to have a really small rectangle, right? And its width will be h, and its height can be modeled simply by f of x, right? It's the height of the function, right? It's going to be so tiny that it's just that height. If we think of a as the area so far function, right? So if we talk about a of x plus h, then we're talking this whole area, right? From here all the way to here. If we subtract from that the area of x, then we're going to be left with the area of this rectangle, right? So that's here. So a of x plus h minus a of x is approximately equal to the area of that little rectangle we added, and you're going to need this, which is, width h and height f of x, so h times f of x. All right, dividing both sides by h, we get a of x plus h minus a of x over h. And we kind of recognize that expression, right? We've seen that a lot. Well, what happens as h tends to 0, right? As we get really small, well, we end up with the definition of a derivative, right? So this is a prime of x. But this is f of x. So a prime of x is equal to f of x. And that gives us the concept of using an antiderivative. So let's take a look at this. We'll just work it with that example. We got the graph. F of x is 2x plus 1. We've got this area. This shape is a. This shape with a pair of parallels. It's a trapezoid, right? So what is the shape? This is a trapezoid. Determine an expression for a of x, right? So we know the area of a trapezoid. So a of x is 1/2 b1 plus b2 over h, or sorry, times h. b1 plus b2 times h. And so we have 1/2. Okay, so base 1. Let's call that base 1, right? What's this value here? It's going to be f of 1, right? That's that height, or sorry, this distance. And this guy here, this is going to be f of x. Okay, so we've got 1/2 f of 1. I didn't write that very well. F of 1 plus f of x times the height, which is the distance between these guys, right? So that's our height. And what's an expression for that? X minus 1, right? Like, what's the distance between x and 1? It's x minus 1. All right, well, we actually have the function, right? So we can work out f of 1. So what's f of 1? Yeah, 2 times 1 plus 1 is 3, right? So we've got 1/2. All right, so f of 1 is 3. F of x is 2x plus 1, right? That's defined. So we've got 3 plus 2x plus 1 times, brackets match, yep, x minus 1. All right, so this is going to be 2x plus 4. We're going to take a half of that, right? So we'll just go with x plus 2. So this is x plus 2 times x minus 1. And we can expand that out. So let's say a of x, this area is x squared minus plus, so x squared plus x minus 2. Okay, that's a of x. X squared plus x minus 2. What happens if we do a prime of x? So there's a of x. What's a prime of x? That's good. Unrehearsed reaction. Right? This happened live, folks. Just like I was watching last night because I told everybody it's community majority. Look at 308.com, and then it starts like PC's 18 and DP6. I'm like, oh no, the same old thing.
308.com.
308.com.
Is that like some Canadian version of
538.com.
What?
Yeah. There's 538 seats in the U.S. Congress, so there's a website called 538.com. Or 538.com.
538.
538.com. And they do predictions about U.S. politics and stuff. And they also do like hockey and baseball. And they do statistics. They crunch the numbers, right? And so 308.com, there are 308 seats in the House of Commons, which is the federal government, right? And so they're going to have to change their name, right? Because there's more seats in the next election.
Should there be a different name for the Alberta one?
It's just that's Canadian politics, so they cover Canadian politics. And 538.com also covers like U.S. Senate elections and stuff like that, right? So it's just, you live in the age where big data is just starting to take off, right? Like it started probably a couple of years ago, but big data is the thing, right? Which relies, funnily enough, on a lot of math. So there is benefit to this. And it doesn't matter what you're going into, right? Like politics, they've been using big data for years. Especially in the States, they know that, oh, you subscribe to this magazine and you live in this area, therefore you vote this way, right? Like that, so we will target you just to make sure that, the thing is get out the vote, right? So I believe the turnout last night was like 57%, which is like better than it has been, but still pretty sad. It's like really 57% of you voted. Anyways.
You're welcome, people watching.
Yeah. We voted.
I didn't.
So a prime of x, it turns out is f of x, right? Well, which we saw, but now we can see that just given a particular practical example, right? Using something. So where does that lead to the next page? So if y equals f of x is a positive continuous function and a of x is the area under y equals f of x from a to x, then a prime of x is equal to f of x, right? The derivative of the area function is the function that generated the curve. So since the derivative of a of x is f of x, we say that a of x is the antiderivative of f of x. So we want to take the antiderivative. So if we want to use a less cumbersome method, right? We want to sum up an infinite rectangles, we don't want to do trapezoids and stuff, we can solve the differential equation. So if we solve a prime of x equals f of x, by solving this for the particular function denoted by f of x, we can find the area under f of x. To solve a differential equation, we need antiderivatives, right? In other words, we need a function whose derivative is this. And when we found that, then what we've got is this. And then we can work out areas. So let's do this again. This time from 1 to 5, we're going to do the same idea, right? Region A of x is indicated. Find the area under the graph of f of x equals 2x plus 1 from 1 to 5 using the concept of antiderivatives. Okay, so what's a of x going to be? It's a function whose derivative is 2x plus 1. What function has a derivative of 2x plus 1?
X squared.
Yeah, so x squared, right? Derivative of x squared is 2x. Gives me 2x. Okay. How do I get a 1?
Plus x.
Plus x. So the area function is x squared plus x, right? How do we check that? Take the derivative of that, we get 2x plus 1. Okay. So we found we need to find a function whose derivative is f of x. And that function is the area function, right? So a of x.
Don't you also need to possibly have a constant? That's what the one on the left.
Yeah, there is. Okay, so when we do the for reals antiderivatives, yeah, that function x squared plus x gives us 2x plus 1. But so does x squared plus x, minus 117. That derivative is also. Okay. Now what's going to happen is when I want to work out this area, right? So the area is what? The area we want, so the area, what did I write here? The area required, right? The area we want is the area 5 minus area 1, right? In other words, the a of x function really gives us from 0 to x. So we'll do a of 5. That gives us this whole area. But we want to subtract off this area, right? So we're doing a of 5 minus a of 1. If the a had a constant on there, which is true, right, then it'll be here minus there. It'll just disappear. Okay, but we'll get into that on the next page when we talk about general antiderivatives. Okay, so a of 5, we got 5 squared plus 5 minus a of 1 squared plus 1. Judicious use of parentheses, right, so that I've just separated out, hey look, here's a of 5, especially because we are subtracting. Okay, which is 2530 minus 1 plus 1 is 2, gives us 28. So that area is 28 square units, right? Now, we could have worked out the same thing by saying, well, f of 1, right, that's 3, and that's 11, and this is 4, right? And so we've got a half of 4 times the sum of 11 and 3, which is 14, and half of 4 is 2 times 14, which is 28. Okay. So you could get that by doing the area of a trapezoid, right? But hey, look at this. And we're not always going to work out nice regions, right? There's not these nice trapezoidal regions. In general, okay, so now, for some reason, we switched from capital A, which had some meaning to me for area, to capital F. I don't know why, but that's what the book uses, and lots of book uses. If F is any antiderivative of the positive function F, which generates the curve, the area under the curve from A to B, so here we'd be looking this particular area, is f of b minus f of a, right? And again, think of f as the function. Oh, that's going to give you the area so far, right? And the area so far, the area from 0 to b is this, and from that we'll subtract the area from 0 to a. So the area under the curve has to be is f of b minus f of a, where f prime of x is equal to f of x, right? So where the derivative of the area is your original function. All right, so let's do a couple of those. Determine the area under the curve of y equals 2x squared plus 3 from x equals 1 to x equals 4. So our first thing to do is say, okay, all right, so I've got the function f of x. I need the function capital F of x, right, which is the function whose derivative is 2x squared plus 3. So how do we get a derivative of 2x squared? So how do we get x squared? What do you got to start with to get x squared?
X cubed.
You got to start with x cubed.
2/3.
Yeah. So when you do x cubed, you know that its derivative is 3x squared, right? But we want to end up with 2x squared. So we got to get rid of the 3. We'll divide that out. But we need a 2, so we'll put the 2 in, right? And then just check this by simply taking the derivative, right? That's 3x squared. 3's cancel. I'm left with 2x squared. Plus, and constants are easy, right? Yeah, plus 3x. Okay, and then, yeah, there is some general constant, but again, that would subtract out because what we're interested in is f of 4 minus f of 1. Okay, so f of 4 is 2/3 times 4 cubed plus 3 times 4 minus 2/3 of 1 cubed plus 3 times 1. Okay, and all we got to do is work that out. So 4 cubed is 64. This would be 128 thirds plus 12 minus 2/3 minus 3. So that's just an expansion and working out some terms in there. I guess if I want to add or subtract these guys, it would help if they had a common denominator, which would be 3. So I'm going to get 128 plus 36 minus 2 minus 9 all over 3. So I give it a denominator of 3, just take the 12, write as 36, it's 36 over 3, and take the minus 3, that'll be minus 9 over 3. And what do we get? We could do 117, 123, 153 over 3, which actually divides out. It gives us 51 square units. So we have 51 square units. Kind of neat, huh? Because we couldn't have done this with, I mean, it wasn't just a trapezoid. Right. I mean, that's a quadratic 2x. Well, it looks like it's a basic quadratic, vertically stretched by 2, shifted up 3 units. And this is also going to work for trig. What's the area under the curve? Y equals sine x from 0 to pi, right? So we can imagine here, here's sine x. This is the area we're going to work out, right? There's 0, there's pi. What's the area? But we don't need to draw that, right? We simply need to say, okay, so the function that I'm given is sine x. I need a function whose derivative is sine x. Negative cos x, right? So derivative of cos x is minus sine, but I want minus sine, so negative cos x, right? Anytime you do an antiderivative, just check it by thinking, okay, the derivative of that would be, yeah, okay. So I've got negative sine x, or positive sine x. And we want f of pi minus f of 0. So that's negative cos pi minus negative cos 0. Okay, now we've got to think of the cosine function. 0, there's pi. So cos pi is negative 1. So we get negative 1. Can't write that very well. Minus negative, and the cos of 0 is 1. So negative 1 is 1, so we got 1 minus negative 1, which is 2. Okay, so 2 units squared. Whatever your units may be. Antiderivatives. All right, so a function f is an antiderivative of little f. So a function big F is an antiderivative of little f on an interval if f prime of x is equal to f of x for all x in the interval. Determine 3 antiderivatives. This is where we get into the thing you said, but you can add a constant, right? So determine 3 antiderivatives of f of x equals 3x squared plus 4x minus 5. And how do those graphs compare? So let's just do one. So what will be the first? So we'll say f of x could be, well, we made life easy, right? Because it's just 3x squared, x cubed, right? Plus 2x squared, right? Derivative of x squared. So, there's strategies and tactics we use to figure these out, right? And the easiest one is when there's powers. Okay, plus 2x squared minus 5x, right? Okay, but what's another one?
The same thing. Yeah.
Same thing. Plus 10. Right? Or the same thing.
Plus 6 or minus 10. Wow.
Say minus 69. Then.
Wow.
phrase that
Wow.
then I have to say nice and see if you get the reference.
What's going on mine too? I don't get it. Could you please explain it?
Apparently it happens on Twitter. Whenever the number comes up, people reply with nice.
Of course.
I don't get it. I just heard that. Some of you, did anybody know that?
Nobody.
That happens?
Never.
No? Okay, well, said,
Who are you following on Twitter?
no, it's my kid. She teaches me all the social media.
Oh.
She's basically said, anytime the number comes up, she's you'd be quoting a hockey stat or something, or Bob McKenzie, was quoting rule number 6, and all of a sudden there's like 300 replies. Nice.
She didn't explain the context.
No, go ahead.
No.
Oh, not suitable for.
Jared,
It's a sex position.
The 7-year-old.
Well, yes, we know.
The 7-year-old genius.
I
You just
totally
learned.
All right, how do all these graphs compare?
Not very well.
The same graph, just what?
Shifted.
Shifted vertically, right? So it's the same graph, only it's shifted vertically. How the graphs are, they are the same. Well, let's say they are congruent. How about that? They are congruent, but shifted vertically. Shifted vertically. Which comes down to the general antiderivative, right? So if f is an antiderivative of f, then the general antiderivative is f of x plus c, where c is an arbitrary constant, right? It doesn't matter what constant you add, right? And if you're using it to calculate areas, it doesn't matter if you added the constant, since it will be, we could back up and say, so we can throw that on there. Then this area here, right, becomes 5 squared plus 5 plus c minus 1 squared plus 1 plus c, and the c minus c. So it's just going to come out in the wash.
So logical.
Yeah. So complete the following. So now we get to spend some time looking at this, right? And we will learn methods for doing these antiderivatives, but for now we can intuit a lot of them, right? Just like, we know. Well, definitely the first column is pretty easy. So if the function is 1, what's a general antiderivative for 1? X. But to make it general? Plus c. Okay, so always remember the plus c. When you're doing an antiderivative, there really is the plus c. K, a constant.
Kx plus c.
Kx plus c. The letter x.
Squared. 1/2 x squared.
1/2 x squared, right? So think about it, right?
GG. We'll leave the class.
Plus c, right? So you say, well, how am I going to get an x? Well, I need to go 1 power higher, right?
Yeah.
So how am I getting an x squared? I need to go x cubed. But when I do the derivative, then I'm going to have a 3 out front. So we got to get rid of that 3, and we'll do 1/3 x cubed.
Wow.
Which then leaves, so if I say x cubed, then you're going to say, well, that's obviously
1/4 x to the power of 4 plus d.
1/4 x to the 4th. So in general, if we have x to the n, where n is not equal to -1, right? You can't have like 1 over n. Well, that's special.
1 over n minus, 1 over n plus 1.
Times,
Over n times x to the power of n.
okay? So that's like the anti-power law, right? So the power rule says you multiply the power by the thing and then reduce the power by 1. And the anti-power rule says you increase the power by 1, but you better divide out that same number because it's going to end up in front. We don't want that. And then if we wanted some other number to come with that, if that was a 2, then we would just throw the 2 in front, right? And then do this. Okay. 1 over x, where x better not be 0. And you can think of that as x to the minus 1, but that's not really going to help. So whose derivative is 1 over x? The thing that's going to turn green and you're going to have to start to mow. Ln x.
Oh.
Now, there's a thing we got to do though, right? Because you can't do the ln of a negative. So we technically have to do the absolute value of x, right? The ln of the absolute value of x, good, that we can do. And then plus c. Plus a constant. Okay, don't forget the constant. Cos x. So whose derivative is cos? Sin x. Plus c. Cos kx. Sine of kx, yeah. But then what do you got to do?
And then, okay.
In that kx,
Whoa.
Times K.
1 over k, right?
How is this?
Chain rule. So think of the anti-chain rule. We will learn the anti-chain rule. But if I do the, so you're going to say sine kx. That's a good starting point, right? Sine kx plus c, right? And then you go, okay, so what's that? Well, it's cos kx. Oh, but then I got to do the derivative of the inner function, which is k. So we got to go 1 over k, right? Or just put this over k. So it's sine kx over k. Okay? And again, just every time you do one of these, just take its derivative. That's the way to check it, right? Take its derivative. Sine x. Negative cos x, right? Because the derivative of cos is minus sine. So it's like, hey, I take the derivative of cos, that'll give me sine. Oh, no, wait, that gives me negative sine. So then I'm going to have to go minus cos x. So sine kx, kind of obvious, right?
Negative 1 over x over k. Right.
Yeah. So negative cos of kx over k plus c. E to the x.
E to the x.
E to the x. Plus c. Right? Derivative of e to the x is e to the x. So the antiderivative of e to the x is e to the x plus some arbitrary constant. E to the kx.
1 over K.
1 over k. E to the kx plus c. EKX over k is fine, right? You can write it as 1 over k times e to the kx. You can write it e to the kx over k. All right, that was the easy stuff. Now we move into slightly more less easy stuff. 12x to the 5th. Well, yeah, so we know we need an x to the 6th. And then, but you got to divide by 6, so divide the 12 by 6, and you get the 2, right? What's the derivative of 2x to the 6th? 6 times 2 is 12, x, lower the power of 5. Minus 2 over root x. Okay, so that's a little bit, minus 4 root
Plus
x.
4 root x.
Whoops. Minus,
Plus 4 root x.
plus 4 root x or minus 4 root x?
Plus 4 root x.
Negative 1/2 and then the negative
Okay, so let's think about this. We have 4x to the half. Now we're trying to figure out, should this be positive? So I'm going to have a half times 4x to the negative a half, but I'll have a positive, so it does have to be negative, right? And then this becomes an x to the negative a half, right? So that the root x moves to the bottom. Okay. But watch the sign, because this was positive, right? So it's a half times 4, which is gives you the 2. X to the negative half gives you the 2 over root x. Got to be a minus, plus c. 4 secant squared x minus sine x. Quick, formula sheet. So 4 tan x, derivative of that's going to be 4 secant squared x, right? So 4 tan x. Sounds like a teacher in this school. 4 tan. Hey, I didn't name him after a trig function. Multiplied by 4. And then we've got a minus sine x. So plus cos x, derivative of cos is minus sine, plus cos x, and to finish it off, plus c. Four x squared plus six, excuse me, plus 6x over 2x.
Why?
Well, what would you? Well,
Simple.
yeah.
Oh.
Really? What is it?
Oh.
So what's this equal to? 2x plus 3.
So
Right?
about it.
You can simplify it. Don't start getting into, oh my god, that means there's a quotient rule and I need the square root of 2x on the bottom so that when I square it I'll get a 2x. No. Okay, so then what is this? Oops. X squared plus 3x plus c. 6x e to the x squared. All right, let's think about this. How do we get an e to the x squared? Well, if you have an e to the x squared, the derivative of that's going to be e to the x squared, right? But then what do you got to do with the x squared? You got to take its derivative, which is going to give you 2x. But we don't want 2x, we want 6x, so put a 3 there, and a plus c there. Okay? So we know that the derivative of e to the anything is e to the anything, but then you've got to multiply that by the derivative of anything. Okay? So if you see an e to the x squared, start with that. That's your basis. And then just say, okay, wait, but that's going to be a 2x. Oh, but I need a 6x, so put a 3 in front. That would be 6x. Good. Negative cos 2x over 4.
I recommend we stop
What?
at the edge. Negative 1/8 of sine of 2x plus c.
Sine of 2x plus c.
Oh.
Okay, check that out. I'm just writing it down. I have no idea if that's right. How do we figure out if it's right?
Probably not.
Well, so we'll take the derivative of sine 2x, which is cos 2x. Okay, good. Times 2. Okay, but we need it to be negative 1, so yeah.
I'm a hero.
You are.
Line here,
I'm saying it wasn't a conclusive goal. That's all there is.
Look, the Anaheim Ducks official Twitter feed tweeted, we have a tie game. Like before the review was done. Right? So they thought it was a goal. Right? And that's the opponents who aren't saying, well, let's wait and see if this obvious goal is called not a goal. And it's like, everybody's really?
They're free to be wrong about that.
But, you
It
know,
wasn't-
hey, stuff like this becomes turning points of series, right? It's like, you could have just said, that's it. Well, we're just going to lose with that. Instead of turning it around, and, hey, we got a 5-on-3. Let's go score, tie it up, and then win it in overtime.
Conclusive proof. That's how
With Backlund getting his first playoff point. Okay, what are we going to do with 2x minus 3 times x plus 4? Expand it.
Yeah.
Right? I mean, what do we got? 2x squared plus 8 minus 3 plus 5x minus 12. Okay, well that's patently easy at this point, right? So we need an x cubed over 3, right? So x squared is going to become x cubed over 3, but we need a 2 in front, so it's going to be 2/3 x cubed plus
5 squared.
5/2, right? Because we just got to, you know, like forget the 5. The 5 is there, right? And then what? Well, we go x squared over 2. So becomes 5/2 x squared
Minus 12x. Wow. Wow.
plus c. 2 cosecant cotangent. All right, so does anything give us a cosecant cotangent?
Yes.
What?
Don't have.
It's on my formula sheet, but it's not in front of me. What gives us cosecant cotangent?
Sorry.
Cosecant. All right, so if we start with cosecant, we know the derivative of that is cosecant cotangent, yeah?
It's negative because
It's negative cosecant. Okay, then we better throw a negative sign in front.
negative 2
But let's leave some room for the 2.
We did it.
Yeah.
Oh my god.
Well, we're almost there.
Oh.
Plus c.
I had like a row of plus C's.
There were already.
Yes, I've written plus C in everywhere. The important thing is remembering to do that when when it's like real and it's not just sort of, hey, what's the,
Well, yeah, I'm just gonna write plus C on line down the whole exam.
Yeah. Well, okay, if you get a table like this, just plus C and then.
Move on.
Yes. Brought to you by that orange soft drink, C plus. It was more Orange Crush last night, yeah. Because, hey, this is Alberta. All right, cos x sine x.
What's the way? Is there any equals that? I don't think so.
Yeah, if we had kind of like is there an internal function? It's kind of like chain rule E-ish.
I don't want to do product rule.
No, think of chain rule, right? Like if I had cosine. So like I need a derivative that's going to give me a cos and a sine.
Right, so negative sine of x. Negative sine of cosine of x.
Well, okay, what's going to give me a cos and a sine? It's like sine squared or something, right?
Yeah.
Can we make this work with sine squared? So let's go sine x squared. What's the derivative of sine x? And that, you could write that as sine squared x, but let's write it this way. So what's that derivative? 2 sine of x cos of x. So we need a half of that.
And a plus C.
And a plus C.
Who's good at math now? Danny.
I did a nice one.
Still not me. I'm pretty shit.
Only on tests, yeah.
Is that cos cubed?
Cos cubed.
Oh, geez.
Yeah, hey, you know that last question, I mean, you could have just done it with similar triangles as well, right? I mean, like, there were two options for it. Trig, fine, right? I mean, it's really the latter problem, redux. But you could also have done it with just similar triangles, right? I got this little triangle here, I got a bigger triangle here, depending on how you name it. Set up a little Pythagorean theorem, derive the heck out of that, and set it to 0 and solve.
Whoa.
Anyways, cos cubed x sine x. Cos cubed x sine x. Okay, so if we're going to get a cos cubed x, then we have to start with a cos fourth x, right? Now you can write that as cos to the fourth x, or you can write it as cos x to the fourth. All right, so we got cos x to the fourth. What's the derivative of that? Well, that's going to be 4 cos x cubed. Okay, good. That gives us our cos cubed x. And then sine x, minus sine x. So we need negative. And we got to get rid of the 4. So negative 1/4, right? Okay. So, we are going to formalize how to find. And then there's huge books on tables of they're called integrals, right? It's the next unit, but antiderivatives, integrals.
Plus C, you crook.
Yeah. 10x.
I don't see a plus C. This is mine now.
Okay. Does anybody have a derivative that gives us tan x? Sec x. What does sec x give us? What's the derivative? It's tan x. Okay. So do we just say secant x?
Plus C.
Plus C.
Yeah, but that gives us secant x and multiply by tan x.
Oh yeah, the derivative of secant x is secant x tan x, right? Okay, so I got to get rid of the secant x.
Secant x over secant x.
Well, okay, well, do we have a function which could give us a 1 over secant x?
Yes.
How about?
Wait, what?
Oh. So what's the derivative of the? So the derivative of ln of secant x is 1 over secant x. The derivative of the inner function secant x is secant x tan x. The 1 over secant x takes out the secant x, leaving us just with tan x.
Game changer.
But if we're doing a ln, it's got to be an absolute value. Yeah.
This could be on the test.
There's other ways to do this, right? So this is the
hard way.
let's kind of intuit our way through this. Can we think of ways to do this? And then there'll be more formal. All right, so how do you do, But, before that, there's always guess and check, say, suss it out, right? And then there's the fallback thing, right? It's like, can I factor this? No, all right, then I'm just going to use the quadratic formula to solve it. Oh, look, I had a perfect square under the square root sign. I really could have factored it, but at this point, And there's the, hey, I can see what that should be. And look, there it is, and I checked it, and it works, right? Because anytime you factor, guess, and check, you always got to check. Same deal here. Anytime you antiderivative by basic, let's see if I can suss this out, check it, make sure that you got what you got. Negative 3 over x.
I think I know the answer.
What?
Negative log of x of the absolute value of
Well,
Negative 3 log x.
Okay, never mind.
yeah, so forget the negative 3, right? It's a constant, so just throw a negative 3 down. And then just say, all right, what is this? Negative 3 times 1 over x. All right, what's the derivative of 1 over x is ln x, right? But when you do ln, you got to do absolute value because lns have to be positive. E to the x plus 1 over e to the x.
I didn't pull up.
Well, so what's the derivative of the first thing? Just e to the x, right? Okay. E to the x. What's another way to say 1 over e to the x?
Ln of the absolute value of e to the x.
Is
Or
Fight me,
E to the negative x.
e to the negative x. Okay, but what's the derivative of e to the negative x? Well, it's e to the negative x times negative 1, right? Derivative of this negative 1. I want this to be a plus, but this is going to end up being a minus, so we're going to toss a minus in there.
Is there a question? Is there a question?
Okay, x squared, square root of x cubed plus 5. So think of x cubed. What's the derivative of, what's the antiderivative? No, what's the derivative of x cubed? 3x squared, right? So we kind of need that inside function, x cubed plus 5, right? And its derivative is going to be 3x squared. So let's start with this, x cubed plus 5. Now, it's to the 1/2, so it had to start out at 3/2. Okay, so let's throw a 3/2 on here, right? Now, what do we get? Well, we're going to get 3/2 times this to the 1/2, so that gives us this bit. And the internal is 3x squared. So we just got to figure out, all right, what number do we divide this by?
Oh yeah, 1/3 and then 3. I think it's that.
Okay, well, let's just do this. So, okay, we got this. That's our starting point, right? And we say, all right, let's just do the derivative of this, and then all we got to do is flip the number around. And so what's this going to be? It's going to be 3/2 times x cubed plus 5 to the 1/2 times 3x squared. So up top I've got 9, and on the bottom I got 2. So let's get rid of the 9 and the 2, right? So up top I had 9, which means I need a 9 on the bottom to cancel it. And on the bottom I've got a 2, which means I need a 2 up top to cancel it. Okay? So basically, you take this guy and you say, well, okay, so what do we have? 9/2 blah. So let's multiply by 2 9s. Okay, and a lot of it's just starting with, it's just recognition of chain rule, right? So, okay, if I start with 3x plus 5, or sorry, x cubed plus 5, its derivative is going to give me a 3x squared. Oh, I see where the x squared came from now. All right, now I need it to the 1/2, so I've got to up that by 1. So then I got 3/2, and then I've got to worry about, okay, but what constant's going to be in there? I shall leave the challenge question for you. Derivative of
How about you don't?
ln x. Oh, we'll talk to tomorrow. We can do it.
No.
All right, so let's do a couple of problems. determine the area under the curve of y equals 6x e to the x squared. Did we do that one? Okay, good. So we've got its antiderivative, right? From x equals 0 to x equals 1. All right, so we start with saying, all right, my function, little f of x. So my big f of x is, what do we say it was? E to the...
3ex squared.
What?
What?
3ex squared.
3 e to the 3x squared? Or?
No, it's 3ex squared.
Oh, 3 times, right. 3 times e to the x squared. Right, okay, because then we get the 2x, which gives us the 6x, and we've got the e to the x squared. Okay, plus c, really, right? All right, what do we we want? So our area is going to be f of 1 minus f of 0. So for now, we'll throw the c in, right? And then you can see how the c... So 3e to the 1 squared plus c minus 3e to the 0. Okay, what's 3 times e to the power of 1 squared? Or 3e to the 1? 3e. So 3e plus c minus, what's e to the 0? 3 minus c. Okay, so now you can see why you don't necessarily need to write the c in here. It's going to be plus here, it's going to be minus there, always, so whatever the constant is. So we end up with 3e minus 3, or you could go 3e minus 1. Okay, square units, and you can work that out. Units squared. Okay, so it's like 3 times 1.8, 2.7, 182, you know, whatever. That's an exact value, right? And you could get a decimal approximation if you needed the approximate. Determining the area under the curve, y equals negative x squared minus 4x. Okay, so starting point, right? We have a function. It's negative x. We can't write, but we have a function. We need a function whose derivative is. So, what might this be? Negative 1, right? Because it's a constant. There's a negative. Okay, negative. 1/3, right? So we got to bump the power from 2 to 3, but we've got to divide by 3. Right? So negative 1/3 x cubed. Okay, so you check that, multiply by 3, gets rid of 3, you get x squared. Okay. Minus 2x squared. Plus c. Right, little general thing. Okay, what do we want? Oh, we want the area under that curve. All right, what's that curve look like? So it's x squared, and it's reflected. No, sorry. Well, it opens down. So it opens down, and all right. So I think we got to kind of sketch this out a little bit, right? Say, okay, so what's going on here? We got y equals negative x squared minus 4x. Well, so let's go negative x and then x plus 4. So let's find the zeros, right? So really what we're looking for is the area of this curve, which is above the x-axis, right? That's what we could figure out. Negative 4, right? Okay, so then this must look something like wait. I don't know how to do this. Sketch this first and put that in. That is
Still right. You also know.
okay. So we're looking for the area from negative 4 to 0, right? That's what we're looking for. So we're looking for the area from negative 4 to 0.
Do you not count?
So we start at the high end, right? And we go to the low end. So it's f of 0 minus f of negative 4. So area. Which is, okay, so we've got 1/3 0 squared cubed, 0 cubed, minus 2 times 0 squared, plus c, minus 1/3 negative 4 cubed, minus 2 negative 4 squared plus c. Like that? Yeah, I think so, right? We just substitute 0 in. So this is 0, this is 0. We just end up with c. Minus, okay, so negative 4 cubed is negative 64. So we got negative 64 over 3. So we've got minus negative 64 over 3. So that'll be plus 64 over 3. And we've got 16 times 2 is 32. So we've got minus negative 32, which will be plus 32. And then we've got minus c.
It should be negative 1/3.
Negative, oh, right. Thanks for that. Okay, so what's that? That's going to make this guy negative then, right? Minus 64. Okay. Thank you. Let's hit that. And we're done, and we'll save this. No, it's wrong. Okay, so we got negative 64 thirds plus 96 thirds, which will be 32 thirds units squared. Or squared units. So 32 over 3. 10 and 2/3. 10.6 repeated. Okay. This is it. Last one. I'll slide that up, let you. Okay. Good enough. Too far. Determine the area under the curve of y equal. Okay, so our function. Well, let's write that. All right, well, do we have to do that? Not really, right? Because we know what it is. Let's go 4 over x. I'm vacillating. Oh, I don't know what he's doing. I'm vacillating. Okay, so the antiderivative of 4. That's just going to be 4x, right?
Yeah, I'm not even Danny. Yeah, I know, I'm telling Danny.
All right, so how do we get a 1 over x? Ln, okay? So this is 4 times 1 over x, right? So it's just going to be minus 4 ln of the absolute value of x. All right, now, so our area goes from the x-intercept. Oh, okay, so we need the x-intercept. X-intercept means that y is 0. 0 is 4 minus 4 over x, so x by inspection is 1, right? 4 minus what gives me 0? Well, 4 minus 4, and 4 exactly. So we need from 1 to e squared. E squared is bigger. So our area is f of e squared minus f of 1. And it's just substitution now. So 4e squared minus 4 ln of e squared. And I'm not going to bother putting absolute value because e squared is going to be positive, right? Minus 4 minus 4 ln 1.
Plus c.
Do we need the plus c? Do we want to keep writing? Like, I don't mind if you don't. Okay, like when you're doing this, if I ask the general antiderivative, yes, you need the c, right? But yeah, when we're doing these guys, we all have this understanding that it's an in and it's a zero-sum game, right? Plus c minus c. Okay, so what's 4e squared? 4e squared. What's the ln of e squared? No, what's the ln of e squared?
Oh.
Or 2, right? What's ln say? It says, what do you raise e to get e squared? 2, I think, right? So remember, the ln says e to the power of what gives you e squared? Let's go with the 2. Minus 4 plus, okay, what's the ln of 1? 0, right? E to the what gives you 1. E to anything to the 0 gives you 1. So plus 0, right? Or maybe I can just write it. If I write it as 4 times 0, at least you can equate the, or you can say, well, it's 4 times something, so that 0 must be ln 1, and then you, oh yeah, ln of 1 is 0. Okay, so what do we got? 4e squared minus 8 minus 4. 4e squared minus 12, right? Which is just a number, right? Because e is just a number. It's not any number. It's Euler's number. Or Euler. I don't know. Hey, timing, like you know, just finishing. That's it, right? There's nothing else on the sheet.